we are looking at is the user interface of Turbo Design 1, which is the 3D inverse design code, and use it to design the rotor for the axial turbine. So following a top-down approach in the main tree, we start by filling in these specifications like the machine type, the fluid properties, stagnation pressure, rotational speed, the number of plates, and for the inlet conditions we can either simply specify the flow rate, or in this case we can import the axial and radial velocity and the stagnation temperature profiles using this option. And then visualize them. And these could be from the CFD or experimental data of the stator exit flow field, for example. Next, we need to specify the meridional shape. Which can again be imported using this option. Along with this 2D grid, which is automatically created. And we can focus the calculations on the rotor blade by limiting the grid extents. And then refine the grid near the leading and trailing edges. And then increase its density in both streamwise and spanwise directions. And the solver is actually a 3D code, and even though we don't have a numerical grid in the tangential or pitchwise direction, it solves the equations using discrete Fourier transforms. And that's why the code is very fast and is numerically quite efficient. Now we support different types of blade thicknesses, such as normal and tangential. And in terms of type, we have the simple constant thickness as well as more complex distributions like Naka profile and flexible control points. And actually this possibility to specify thickness as part of the inverse design is very useful because it guarantees structural integrity. And if you have some existing thickness profile, then you can import that as well using this. Now, blockage is something that we use for cases for significant boundary layer blockage such as Sirocco fans, so we can skip that for now. And then we specify some fluid dynamic inputs, which is the blade loading, and this is the most important parameter for the inverse design method. Here we first specify the spanwise RVT star, which is the swirl distribution from hub to tip, and this can again be imposed from CFD or experimental data at the rotor inlet and exit using this option. Here 0 spanwise location is the hub and 1 is the tip, and we are imposing this at the leading edge and trailing edge of the blade row. Now since the rotor leading edge distribution is the same as the stator trailing edge data, this automatically ensures a good matching between the two components. And at the trailing edge, of course, the swirl is reduced as the blade extracts work from the fluid. And if you recall the Euler turbomachinery equation, the difference in RVT star between the inlet and the exit gives you the specific work of the blade row. And this is important because it means that every design coming out of TD1 respects your required duty point. Now that the overall blade work is fixed, we need to specify how it varies from the leading edge to the trailing edge at the hub and the shroud sections. And for this we have the streamwise blade loading, which directly controls the blade surface pressure distribution. And we can either go with the default settings or import it from another case like this. And this is basically the derivative of RVT star, and it directly relates to the pressure jump across the blade. So here we have a parabolic section from the leading edge to a point here, which you can vary, a linear section between these 2 points, and from this point to the trailing edge there is another parabolic section. And the loading at this point defines the incidence at the leading edge, and at the trailing edge the loading is always 0, which satisfies the kata condition. And so these 4 settings you can easily parameterize the 3D blade loading for manual adjustment or automatic optimization. And you can also add an extra section if you wish to specify the loading at the mid-span for better control of this high aspect ratio blade. And then the last important parameter is the stacking condition. And so on one quasi-orthogonal at some streamwise location, which is 0 for leading edge and 1 for trailing edge, you actually specify the variation of wrap angle from up to tip, and in that way you can lean the blade, and this will create a span-wise pressure force or gradient. And this is something that you can also use to additionally influence the 3D pressure field. But for now we can continue with 0 or radial stacking at 40% of the axial chord, which is close to its center of mass and helps to balance the centrifugal force. And finally, in the solver section, we can reduce the initial blade number to avoid too much blockage. And we can leave everything else to the default settings. Now, even though the program is fully 3D, it runs very quickly within 10 seconds or so, and it gives you the blade geometry and also quite an accurate inviscid flow information. And this information is something that we can use to iterate on the design. So we can first take a look at the converged rotor geometry using this 3D plot here. And then we can also create 2D plots of, let's say, surface Mach number. at the hub, midspan and the shroud. And in our experience, when we compare surface pressure from TD1 versus that from CFD, we get a very good match even though TD1 is inviscid. And that's because the viscous effects don't really impact the static pressure field, and they do distort the velocity field, but we can relate the isentropic Mach numbers and velocities to some performance parameters, which we can use to explore the design space. And you can see these performance parameters here in the project manager window. Such as the indicators of maximum surface Mach number, diffusion ratio, profile and end wall losses, throat and maximum lean, and also some mechanical parameters like the centrifugal stress and the cross-section area near the hub. And next we can choose to see only the selected parameters like this. And finally, the selected design can be verified with CFD and FEA analysis, and for this the geometry can be directly exported from Turbo Design 1. To different format files that are needed for the mesh generation, such as curve files for TurboGrid or step files for ANSYS Mechanical.